In this video, we're going to discuss the electron affinity. The electron affinity is defined as the energy released or absorbed when a neutral atom in its gaseous state gains an electron to form an anion. So here we have a generic formula where we have some atom in its gaseous state. We add an electron to form a negative anion. Now the addition of an electron may either release energy, and we call that an exothermic process, or the addition of the electron may require or absorb energy. We call that an endothermic process. The more negative an atom's electron affinity, so the more energy is released when an atom accepts an electron, the more readily that atom will accept an additional electron. So if we added an electron to some atom and it had a very negative electron affinity, that indicates that that atom will accept that electron very readily. So it's very likely to form an anion. Conversely, if you add an electron to an atom and it has a very small negative or positive electron affinity, that indicates that that atom is less likely to accept an additional electron. Therefore, atoms which have very low electron affinities or positive electron affinities are less likely to form anions and more likely to form cations. Now, there is a periodic trend for an electron affinity, which we need to be aware of. Electron affinities on a periodic table tend to increase as we move across a period, decrease as we move down a group, and they decrease from group 7 to group 8, so from the halogens to the noble gases. So if we look on our periodic table, in general, as we move from left to right across a period, the electron affinities increase. Now there's a few exceptions to this, and we'll talk about those in a future video. And as we move down a group, the electron affinity tends to decrease. Also, as we go from our halogens to our noble gases, there's a large decrease in the electron affinity. So in other words, as we move from left to right, the atoms are more likely to accept an electron. As we move from top to bottom, they are less likely to accept an electron. Okay? So be sure you're familiar with these general trends. Now, what we want to do is explain why these general trends occur. So maybe you want to pause the video and think about it and see if you can come up with an explanation for these trends. So the electron affinity for an atom is related to that atom's effective nuclear charge. So as we move across a period, we know that the atom's effective nuclear charges increase. The outermost valence shell electrons experience a greater attractive force towards the nucleus. Of course, as we move from left to right, the shielding value tends to increase very slightly relative to its actual nuclear charge. This causes the effective nuclear charge to increase. So what does this mean? Well, the greater the effective nuclear charge, it makes it easier to add an additional electron to the valence shell. So as we move from left to right across a period, the effective nuclear charge increases. Therefore, the attractive force felt by those outer electrons increases, which makes it easier to stick another electron on there. So if we add an electron as we move across from left to right, more energy is released. Now, as we move down a group, the electron affinity decreases. Why is this? Well, as we move down a group, we know that a new valence shell is started, which increases the valence electron's distance from the nucleus. An added electron to this valence shell, so if we add an additional electron to the valence shell, this electron would be farther from the nucleus and therefore would experience a less attractive force. So it's going to be held less tightly. Therefore, as we move down a group, less energy would be released, indicating that the electrons are less likely to stick to that atom and form an anion. Another way to put this is that as we move down a group, the atoms get progressively lower in their electron affinity, or less negative. Also, we mentioned that when we go from group 7, the halogens, to group 8, the noble gases, the electron affinity decreases. So if we look on our periodic table, the electron affinity generally increases. Again, there's a couple of exceptions. It generally increases as we move across, and then when we go from fluorine to neon, there's a big increase. The same thing with the period number 3. As we go across, it tends to increase up until we get to chlorine. When we go from chlorine to argon, again, there's a large drop in the electron affinity. Now, what that indicates is that fluorine, chlorine, bromine, these guys will very readily accept an electron, but the noble gases are very unlikely to accept an additional electron because they have a very low electron affinity. So, why is this? Well, the added electron to group 7 would fill up its valence shell. The added electron to the halogens would therefore experience a large effective nuclear charge, making it very likely to stick. Let's look at an example. Let's say fluorine. Here is the electron configuration for fluorine. Fluorine has one empty space in its valence shell. So if we add an electron to fluorine to form fluoride, so here we have fluorine, here we've added the additional electron, that electron would go into fluorine's valence shell. That electron would experience a very high effective nuclear charge because, again, there's only very few core electrons relative to its actual nuclear charge. So this electron would feel a strong attractive force towards the nucleus and would therefore stick very readily, forming the fluoride ion. Therefore, we would have a very large negative electron affinity if we added an electron to fluorine. Well, what about if we looked at the noble gases? We said there was a drop. Well, let's look at neon. When we add the electron to neon, the additional electron, the added electron, experiences a very small effective nuclear charge. So let's look at the electron configuration for neon. Here we have it. Again, neon has a full valence shell. So if we add an electron to neon to form the neon anion, or Ne-, where would that electron go? Well, of course, it would start a new valence shell. So this added electron would experience a lot of shielding because now that added electron is shielded by all of these what are now core electrons. Now we haven't added any more protons, so when we add an electron to neon to form the neon anion, the added electron experiences a great increase in the shielding, but its actual nuclear charge does not increase. So therefore, this electron would have a very small effective nuclear charge, a very small attractive force towards the nucleus, indicating that that electron would not want to stick to neon, and therefore we would have either a very small negative or maybe even a positive electron affinity value, indicating that neon will not readily accept an additional electron. So let's be sure we appreciate these periodic trends that we discussed. Be sure you can discuss them in terms of effective nuclear charge.